who's here as a candidate in connection with our climate data analytics position. Great to have him here. He's currently an assistant professor at Princeton, and David has a PhD in applied physics from Harvard in 2006, and he completed a postdoc at Duke. And I won't go over his vita, but he has an extensive publication record. You can take a look at his vita, 30 papers plus several in press, and extensive work both with his current team and today I think we'd like to present some of his work on Amazonian deforestation. So my pleasure to welcome David, and the floor is yours.
Okay, thank you. Okay, so thank you all for having me here today. It's been a terrific visit so far, and I'm excited to have the opportunity to talk to you all. So today I'm going to be talking about regional climate changes through the 3 decades of Amazon deforestation. And so why Amazonia? Why is this an interesting place? I think people from many different disciplines would find Amazonia interesting. Hydrologically, it's the largest watershed in the world. It receives a tremendous amount of rainfall, varying across the basin, but about 2.5 meters per year on average. And it corresponds to about 20% of the global freshwater discharge. Ecologically, it contains almost 10% of the total world species, over 40,000 different plant species. Biogeochemically, the Amazonian rainforests are storing about 120 petagrams of carbon, and so considering that anthropogenic CO2 emissions from fossil fuel combustion are only 8 to 10 or so petagrams per year, that's a large number. And there are also very complex human-natural ecosystem interactions going on in the Amazon right now, one of which is deforestation. Maybe I could lower the lights here.
Experiment. Pick one. The middle one, I think, is a good one.
Like we just saw.
Okay, is that okay? That's fine. Yeah. Okay. And so you have an image of the Amazon basin here with the red areas indicating regions that are already deforested. If you add up the area, it's roughly 20% or so. And deforestation is continuing. You have this nice little movie based on Landsat imagery showing you how deforestation has increased in the southwestern Amazon. It's the Brazilian state of Rondônia. In the early 80s, it was basically just a strip along the road, but as time went on, it goes to fill a large amount of space. And so this deforestation is going on. Why is it important? Well, there are many reasons why you could argue that this deforestation is important. It's certainly linked to economic activity. It could either increase or decrease economic activity. It's linked to climate. It affects evapotranspiration. It affects, it affects runoff. It affects your plants, your biodiversity. It affects fires, and all of these changes in the hydroclimate and in the ecosystems go on and feed back to the human system through effects like flooding, changes in agricultural and economic productivity, perhaps changes in respiratory disease incidence, and changes in water availability. And so there's quite a complex set of feedbacks and interactions here. For the purposes of today's short seminar, I'm just going to focus on the climatic or the hydroclimatic impacts of Amazonian deforestation. And so what are they? What's the basic idea? If you take a patch of tropical rainforest, you could construct a simple energy budget. So I have my atmosphere above my land, and what are the basic energetics? Well, you have a certain net amount of radiation coming down from the atmosphere to the land, and that energy could be spent in various ways. One important sink of that energy is evapotranspiration. So you use that energy to evaporate water, and that's represented by this latent heat flux. And this is a fairly large term in your typical tropical forest energy budget. Another way you could spend the energy is to increase the temperature of your atmosphere, and that's represented by this sensible heat flux. Or you could also affect the temperature of the land surface itself, and that's represented by this storage flux. And so if you take this nice patch of tropical rainforest and you go ahead and deforest, you change this energy budget. First of all, you reduce the total amount of energy to the system. That's a reduction in net radiation, which occurs because the albedo increases. It's larger over pasture and agricultural land as compared to rainforest. The second major change is that you greatly reduce the latent heat flux, the evapotranspiration. And so that's in part due to the reduced energy input, but it's also because you have fewer leaves covering your land surface if you have pasture or crops compared to a multi-layer tropical rainforest canopy. And also you have completely different rooting systems with the roots in rainforests having access to potentially deep water, whereas if you have grasses, you have roots that have access to a shallower layer of soil and soil water. And so your evapotranspiration goes down, but the amount of energy that's spent to increase the temperature goes up. And so you generally wind up with a warmer patch of land. And so what does this mean for climatic variables that we tend to think about, like temperature and precipitation? Well, if indeed the dominant effect is that you have a warmer patch of land under deforestation, you have warm air, and so it'll rise. As that warm air rises, it creates a pressure gradient, and air rushes in from the sides to fill up the space. The air that rushes in from the sides comes from the neighboring rainforest, and so it's relatively wet. And so you have a situation where you have wet air coming in from the sides, rising due to the higher temperatures, and potentially cloudiness and rainfall. So this is the theory of what happens when you cut down a small patch of rainforest. This has actually been observed. In particular, there have been remote sensing satellite observations of albedo, and that's what's shown on this nice mainly blue graph here. And so this area corresponds to the deforested state of Rondônia in Brazil, with the map on the right showing the Landsat land cover. And so you have hot spots of albedo that are interspersed over this deforested landscape, and that increase in albedo is interpreted to mean an increase in cloudiness. However, if you go on and you cut down more and more rainforest, the basic dynamics of this situation may change. And this was suggested some time ago, where through some basic model simulations, groups have studied what happens when you may cut down patches of landscape of different sizes. And so in this particular study, they used a two-dimensional atmospheric model, pretty basic, and they introduced these sensible heat flux anomalies that correspond to deforested patches of land. And so when you have deforestation that's occurring on about a 2-kilometer scale, they simulate convection. What that means is that you have upward motion of air over that deforested patch of land, and that upward motion of air brings with it water vapor, and that water vapor eventually condenses and forms clouds. And so the idea is that you have increased cloudiness. As you deforest larger and larger patches of land, it's been simulated that you have stronger convection and presumably stronger cloudiness. However, if the scale of deforestation gets too large, and in this particular set of simulations about 40 kilometers, the amount of convection gets smaller. And so this suggests that there may be an upper limit to this effect, whereby if you increase too large an area of land, you'll no longer get this increase in cloudiness and potentially rainfall. And so certainly over the past 30 years, there have been dramatic changes in the spatial distribution of deforested patches in Amazonia, and in particular in the state of Rondônia, where you go from very small-scale deforestation to deforestation that's much more widespread. And so the basic question that I want to address today is what is the climatic syndrome of contemporary deforestation? Is it the conventional picture that I presented at the beginning, where you have cloudiness and rain over deforested patches, or might the situation have evolved into something new? And so I'm going to begin by showing analysis based on satellite observations, and I'm going to pull together several different data sets to show you. So first of all, what has to feed into this is some understanding of how the land cover has changed in time, and that comes from Landsat data that's available since the 1970s, but for this particular region, the quality is best from the 1980s onward. And so, coupled with that land cover data, I wanted to present you with some metric of cloudiness. And so how do we infer cloudiness over these remote regions of Amazonia? Well, we use satellite information to observe the Earth, and based on the satellite observations, try to infer what the cloudiness had to have been. And in particular, we use two metrics, the albedo, with the idea being that bright patches of landscape are more likely to be cloudy, and the brightness temperature, which is some measure of thermal infrared emission, whereby you have lower temperatures if emission is coming from a higher level in the atmosphere corresponding to clouds, compared to if you're at the surface, which is presumably warmer. And so the brightness temperature and the albedo get fed into a standard cloud detection algorithm to determine the cloudiness status of a particular pixel at a given time. And this cloud algorithm runs all sorts of tests, so that for a pixel to be deemed cloudy, it has to have an unusually high albedo and low brightness temperature relative to itself over a certain period of time, and also relative to its neighbors. And so I'll go through some of these data sets. And so first, here's some more of the Landsat data showing the deforested areas in the middle of the 1980s, 90s, and 2000s, with the bright color showing deforestation. And you can see how it's spread. I've just drawn by hand in black there in outline approximating the deforested region just to guide the eye. And then Next, I want to give you some sense of how this cloud detection algorithm works. This is just a snapshot from a particular day, August 1st, 2008, at a particular time, 2 p.m. local time. And here on the left, it's showing the albedo. You have mostly blue, which represents low albedo, but you have some hotter spots of high albedo. In the center, you have your brightness temperature, which is mostly red, which is warm, but then you also have a few darker blue patches. And so that information gets fed into this cloud detection algorithm, and you come up with the binary map on the right with the white areas representing clouds at this particular time. And so you can aggregate this information over all pixels and all times, and this is for year 1985. And this shows you the general distributions of albedo and brightness temperature that are associated with cloudy pixels and clear pixels. And so it comes out that, as you would expect, your clear pixels generally have lower albedos than your cloudy pixels, and the clear pixels have higher brightness temperatures than your cloudy pixels. All right, and so now we come to the first really interesting result, which are the cloud cover maps for the 1980s, the 90s, and the 2000s that we derived from aggregating all this cloud information together. And so here, again, to guide the eye, I superimposed these black sketches approximating the outline of the deforested region. The solid lines represent the deforestation in each particular period. The graph on the left and on the center also has a dashed line, which corresponds to the late period 2001, 2008 deforestation. So here you could see how the cloudiness has changed in the deforested area. In the 1980s, you can see a hot spot of cloudiness sort of along the central channel, that deforested area, which actually almost corresponds exactly with the road that cuts through there. And so this is very consistent with the conventional theory that we have an increase in cloudiness over deforested areas. I think the picture changes a little bit in the 1990s. If you look at the deforested area and where the clouds are, you tend to see the clouds clustered maybe a little bit more to the left, to the west in this diagram. And as you move to the 2000s, it's even more pronounced that the western part of this deforested area is cloudier than the eastern part. And this is a little bit of a surprise. There's nothing in the earlier theories that would have suggested this pattern that, you know, if you just look at it with your eyes, it seems like there's some sort of dipole here. One thing I should have pointed out is that here I'm showing that the anomalies relative to the regional mean in each case. In other words, I'm not worried about long-term trends in cloudiness that may be driven by multi-decadal modes of climate variability. I'm just interested in the spatial patterns. And so, motivated by this dipole-like pattern, I just went ahead and calculated a formal dipole moment of cloud anomalies for each year in my time series, calculated in the conventional way as you might in a physics class. So there's no monopole term here because I'm dealing with anomalies relative to the regional mean. So there's just a pure dipole moment. The conventional idea would be that there should be no dipole, that you would just get increases in cloudiness over the deforested region without any preferred spatial direction. And so when you put together a time series of what this dipole moment, or the magnitude of this dipole moment looks like, I think you see something very interesting. So we go back to 1983, which is the earliest year that we had good cloud data for, up to 2008, which is the latest year which we had the cloud data for. And immediately, you could see an increasing trend in this dipole moment, the spatial distribution of cloudiness. Where in the early period, when deforestation was just beginning in the 1980s, this dipole moment was very small, and then it increases by a factor of a few, at least, by the late period deforestation. And then in the inset, I drew the dipole vector for each year, with the different years being color-coded to the different dots in the time series. And again, that sort of brings out, if you look at the blue arrows, which represent the early period, that the dipole's relatively weak. As you move to the later periods, it gets stronger and stronger. And so this suggests that there's something going on associated with contemporary deforestation in the Amazon that is affecting clouds and perhaps the hydroclimate there. And so the next thing that we wanted to do was to figure out if we may also be able to observe changes in precipitation over the Amazon. In particular, this deforested state of Rondônia. So this is a challenge, and in fact, I don't think there's any foolproof way of doing that, because there are just limited observations going back to the early 1980s. Certainly, there's not a high spatial density of rain gauges with homogeneous data coverage over this region, so we don't have the ground data. Again, we have to, one thing that we could do is fall back on satellites. And so there are different satellite-derived precipitation products, and I think that by itself, no one of them is actually perfect for this analysis. There's the TRIM, which is nice because it's completely independent of this cloud data, but the problem is that it really only covers the second half of the cloud time series. We don't have complete overlap, and in particular, we would not be able to capture the early period. There's a new climate data record, the Persian precipitation product, which also has its pluses and minuses. On the one hand, it does have full overlap with the cloud data, but on the other hand, it's not completely independent of the cloud data. There are several things that feed into this precipitation product, and the cloud data is one of them. The third tool that we could use are models to try to understand this change in cloudiness. They also, the good thing about models is that they would be completely independent of the cloud data, and you could potentially have perfect overlap. But on the other hand, you also have all the problems and uncertainties that are associated with models to deal with. And so my strategy was to not rely on any one of these things by itself, but put them all together and see where the balance of evidence leads us to. And so first, the TRIM. So this is a map of precipitation from TRIM averaged over 2002 to 2014. You can see a pretty clear spatial distribution with your reds in the west and your blues in the east. Sorry, we lost the scale on this diagram, but in fact it's the reds that are relatively wet and the blues that are relatively dry. And so that would sort of make sense with the late period cloud observations, with the western part of the deforested area being relatively cloudy and wet, and the eastern part of the deforested area being relatively dry and clear. But unfortunately, we don't have data going back to the early period, so we can't tell if this is just the standard pattern that you'd expect in every year, or if this represents some sort of change. So go on to the next data set. It's the Persian climate data record, which does go back to the early 1980s. Here, again, I separated the maps out into 3 time periods, the 80s, the 90s, and the 2000s. And if you look at these maps, I think that you could see some evolution in the spatial pattern in the deforested area. In the 1980s, it's actually, there is certainly some variation in the deforested area, but it doesn't look that different from what's going on in the non-deforested area. And so it's not clear to me that there's anything actually going on there in that map. But by the time you get to the 1990s, you do see a little bit more clearly the yellows and greens accumulating on the western portion and the blues on the eastern portion. And in the 2000s, I think it's very clear that you have the reds in the west, so wetter west, and the blues in the drier east. And so since we're able to construct the full time series using this Persian precipitation product, you could overlay the computed precipitation dipole on the computed cloudiness dipole and see how they match up. And that's shown here. So this is just an augmented version of the graph that I showed you before. Your time series going from 1983, here extended out a little bit to 2013, with all your colored dots representing the exact same colored dots that I showed you before of the cloudiness dipole. But now I've also added all these gray dots, which represent the precipitation dipole derived from the Persian. And if you look at what's going on with the precipitation, you do see a nice increasing trend throughout most of the time series, which seems to be consistent with the cloudiness information. And so, in a sense, that's consistent. One thing that's a little curious, though, is if you look at the end of the time series, the precipitation dipole seems to stall out. So what could be happening there? We scratched our heads a little bit, but then we pulled up this figure showing the deforestation rate in Rondônia. And if you look at the deforestation that's been going on and how it's changed over time, the deforestation actually also stalled out in the middle of the 2000s. And so maybe it's no big surprise that the precipitation dipole didn't change so much, since the deforestation didn't change so much in those very latest years. And so, taken together, I think that these observations suggest that the hydroclimate of Rondônia, this deforested area, has changed, with the west getting wetter and cloudier, and the east getting drier and clearer. And that's about as far as we could go with the observations. And so our next step was to think about how we could use models to answer further questions. And so in particular, I wanted to see if our atmospheric models could simulate this dipole, and whether or not simulations with deforestation had a dipole and simulations without deforestation didn't have a dipole. Secondly, if we could detect a deforestation signal in our climate model simulations, we ought to be able to probe the model and figure out the exact mechanism that's leading to this change in precipitation precipitation and cloudiness patterns. So these are our next two objectives. To address these questions, ocean land atmosphere model, which in this analysis I use purely as an atmospheric GCM, general circulation model. And so it would be forced with whatever sea surface temperatures that you prescribe and whatever land cover that you prescribe. And the task of this model would be to simulate the atmosphere. It's a variable resolution model with the unstructured grid mesh. You can see in this particular case, it's an example with very high resolution over the Amazon. And so the point of doing that is that you could have very high resolution in regions of interest, coarser resolutions in the far field, and because your resolution is still coarse in the far field, your computational time stays relatively low. So this variable resolution approach is a way to get good bang for your buck. We've tested out this model in several previous studies focusing on the hydroclimate of Amazonia. I'm not going to get into the details of model evaluation here. Instead, I'm just going to just try to stick to this main question regarding the dipole and deforestation. And so we set up a particular simulation design to query the model as to whether deforestation can cause this type of dipole in the late period. And so our focus was on the dry season months when this dipole is observed to be strongest, and in particular we're just focusing on August. Carried out 24 time-lagged ensemble members so we could get some decent statistics. Our grid resolution was 8 kilometers near Rondonia so that we could adequately resolve the different deforested patches of land. And then we carried out a factorial experiment where we adjusted both the land cover and the sea surface temperatures to control for natural climate variability. And so our land cover experiments consisted of representations of Rondonia with a pristine forest untouched by humans. We carried out simulations with the 1986 land cover map representative of the early period, and then with the 2006 land cover map representative of the late period. And then we coupled these land cover variations with different configurations of sea surface temperature, focusing on the 1980s average, the 2000s average, and then a longer-term 40-year average record. This is what our model grid mesh looked like in the vicinity of Rondonia. You can see a little deforested patch of land there. We carried the high resolution grid a little bit more to the west than to the east so that we could do a better job with the topography that's out there. And as you move away from the deforested area, the grid resolution gets coarser and coarser. Here I'm only showing part of South America, but this is in fact a global model, and the grid expands to cover the world. And so in model world, what are the differences between deforested patches of land and pristine forest? Here I've listed the 5 key differences. I put number 1, the roughness length, the surface roughness of the surface changes. Forests tend to have a rougher surface, and pasture is more smooth. This roughness length could actually change by almost 2 orders of magnitude compared to pastures to forests. The albedo changes. Pastures have a higher albedo. Rooting depth of the vegetation changes. Leaf area index is higher in forests than in pastures. and the model resistance changes. So what do we expect from these simulations? Well, we're dealing with model world, which has its pluses and minuses. We're able to control these experiments pretty well. But on the other hand, like other GCMs, this model has limitations. In particular, even at 8-kilometer resolution, convection has to be parameterized. It can't be resolved. And so trying to accurately simulate cloudiness itself is probably out of reach. However, we could look at other metrics of the hydroclimate, of the simulated hydroclimate, including things like relative humidity, precipitation, wind fields, and other variables. So I'm going to start with relative humidity then. Near the top of a typical daytime boundary layer in Rondônia. And so this compares the simulated relative humidities from simulations with 1980s conditions compared to 2000s conditions. In the 1980s, you tend to have increased relative humidity along the central spine of the deforested area. In the 2000s, you could see the beginnings of this dipole starting to occur, with the red areas clustered, mainly along the western side of the deforested area, although you do see a little patch of red in the east. And so if you had nice atmospheric measurements of relative humidity over this region in this period, this is what you might be able to compare such observations to. Unfortunately, such observations don't exist, so we can't make that comparison. We could dig a little bit deeper to try to understand exactly what the role of deforestation is in causing these patterns. And so I carried out the third set of simulations where I ran with a pristine forest and subtracted off the pristine forest from these simulation results to determine the deforestation effect in both the 80s and the 2000s. And that's here, what's shown here on the bottom. And so this now is showing the change in relative humidity from pristine forest conditions. And here I think it's apparent that in the 1980s in the central, along the road in the deforested area, you have positive relative humidity anomalies, which is consistent with the increased cloud cover. And in the 2000s, you have an even clearer signal of deforestation along the western half of this deforested area, with this hot spot in the southeast actually becoming a little bit weaker. These relative humidity patterns actually have little sensitivity to the sea surface temperature regime. And so we wanted to see if long-term changes in sea surface temperatures or decadal trends in sea surface temperatures might be partly responsible for this dipole, but that doesn't look like it's the case. If you force the model with the 40-year average sea surface temperatures, you basically get the same results for your relative humidity field. All right. So we're able to look at other variables simulated by the model. This is precipitation. So this is the precipitation that's simulated for 86 land cover and for 2006 land cover. And so in principle, these types of graphs could be compared to precipitation observations if we had them. And in 1986, the model's showing right in the center of the deforested region, a strong positive precipitation anomaly. And in 2006, we have a positive precipitation anomaly in the west and a negative precipitation anomaly in the east, which is consistent with both the TRIM and the Persian precipitation products. And so I think taking the observations and the model together, we're coming up with a consistent story. Here, what I did was compute the dipole in the 2000s, and I computed the dipole in the 1980s, and I computed the amplification. So how much larger is the dipole in the 2000s than the 1980s? And I put on this graph the simulated relative humidity, where you see the simulated dipole goes up by about a factor of 3. There's some spread there, which is actually the spread among our 24 ensemble members. So it's some measure of uncertainty. Simulated precipitation also goes up by a little bit more than a factor of 3 in terms of its dipole. The observed cloudiness dipole goes up by more than a factor of 3. And the observed precipitation dipole from the Persian goes up by about a factor of 4. So very consistent picture. And so we see this hydroclimate dipole cropping up in the observations in the model. And so we really wanted to know what it was about deforestation that gave rise to this spatial pattern. And we carried out a similar set of experiments to what I showed you before to try to answer that question. Just to simplify it a little bit, again, we carried out ensembles of model simulations. But in this case, they were all forced with the long-term average sea surface temperature, just for simplicity. We carried out simulations with heavy deforestation, the 2005 land cover, and compared it to a case with no deforestation, pristine forest. And then finally, I'll get a little bit more into this at the very end. We also considered cases where in our deforested landscape, we artificially kept the albedo at the albedo of pristine forest. And we did additional simulations where we artificially kept the roughness length at the roughness length of pristine forest to try to isolate the role of these different land cover variables in contributing to the simulated dipole. And so what we first did was take a look at the dynamics of the atmosphere that were simulated by the model, and I think this is actually where the most interesting results lay. And first I want to focus on the vertical winds that are simulated by the model. And here the idea is, as I mentioned earlier, that if you have positive vertical winds, it's associated with rising air where the water eventually condenses and forms clouds and precipitation. So positive vertical wind anomalies, you think increased cloudiness. Negative vertical wind anomalies are the opposite. Sinking air, dry air, suppressed cloudiness. And so this is the vertical wind anomaly that results when you take the difference between your deforested simulation and your pristine forest simulation. You could think of this as the effect of deforestation in model world, where we've deforested this gray outline here. And so the colors show the difference in the vertical wind, and you see the blues clustered along the left. That's the rising motion, the anomaly in the rising motion, which we would generally associate with clouds, and the red in the east, the sinking motion that we would associate with less clouds. The horizontal wind anomalies are shown by the arrow, and then at the right-hand edge, I'm showing the direction of the ambient winds. So the winds are basically easterly. And so this is, again, consistent with the dipole that was simulated. And you see that deforestation actually may be causing some sort of anomalous circulation to develop. These are similar sorts of graphs of vertical wind differences, and the arrows of horizontal wind differences, but at different layers of the atmosphere, focusing on the atmospheric boundary layer, daytime boundary layer. With the lowest altitudes at 515 meters in the upper left, going up to about 1,500 meters in the lower left. And at the lowest levels of the atmosphere, you can see there's still a lot of noise, but between about 1,000 and 1,500 meters, you see this nice circulation develop where your horizontal wind anomalies are actually basically easterly or northeasterly at the lower levels, and then you can see the return flow coming back aloft. And then this final panel shows the directions of the ambient winds at the different levels. And so you have this nice circulation developing. If you integrate in order to test the net effect of this circulation, you might be interested in the net convergence or divergence that arises. And so we integrated the horizontal divergence from the surface up to 1.2 kilometers. And here it's very clear that we have negative divergence or convergence in the west, and positive divergence, the blue colors, in the east. And so this dipole seems to have a dynamical origin here. And so what would cause this sort of circulation, this sort of dynamic? Here's our suggestion. We propose that the changes in the roughness length lead to dynamical triggering and this dipole circulation. And so if you have winds coming in from the east from a rough surface to a smooth surface, that change in roughness will affect your momentum fluxes, and your near surface winds may accelerate as you reduce the friction. As your winds accelerate, that would, through mass conservation, lead to sinking motion. And then as your winds traverse from the smooth areas to the rough areas, you would have an increase in friction. That would also affect your momentum fluxes, but in the opposite way. That would slow down your wind, you'd get convergence, and by mass conservation, you would have upward motion. And so your anomalous circulation would look something like this arrow, with the sinking in the east, rising in the west, with increased cloudiness and precipitation. And so we could test this idea in model world by designing simulations that had specific perturbations to the surface roughness length. And in particular, we came up with a deforested simulation that treated almost exactly like a conventional deforested simulation, except we did not reduce the surface roughness. We kept the surface roughness the same as the pristine forest. And then we compared this simulation to our pristine forest baseline. And according to the proposition that I just presented, our expectation was that since there was no change in the roughness length, there would be no dipole. And that's pretty much exactly what happened. This is again showing the wind anomalies, the colors show the vertical wind anomalies at two particular layers in the atmosphere, in the boundary layer. And within the deforested area, you may have some slight negative anomaly on average, but there's certainly no partitioning between the east and the west. So without this surface roughness change, the dipole vanishes. Looking forward, there are a few things that we're quite curious about now. Unfortunately, in our model simulations, we had to use a convective parameterization. I think we are on the verge of having the resources and are able to construct cleverly enough designed simulations so that we could simulate at least a few seasons at a 1 kilometer or even better resolution, and actually try to resolve the cloudiness and remove all the uncertainties associated with the convective parameterization. We're also interested in the year-to-year and the seasonal variability of the dipole, and so what's the interaction between these local and atmospheric exchanges and the larger scale atmospheric circulation. And we focus only on one part of the Amazon, but we're wondering how this might generalize to other deforested regions. So just to conclude, the takeaways are that observations have suggested a development of a hydroclimatic dipole over Rondônia over the past 30 years of deforestation, with the west becoming wetter and cloudier, the east becoming drier and clearer. Numerical simulations are able to simulate this and indeed implicate deforestation, and surface roughness changes in particular is the driver of these changes. And this dipole effect is fundamentally different from the previously proposed mechanism of simple thermal triggering, where you have rising hot air and moist air rushing in from neighboring forests to give you clouds over deforested areas. So finally, I have a picture of one of my PhD students up here who was responsible for carrying out many of these simulations. Also want to thank my collaborators and sources of support. And thank you all for listening to me.
So what do you think? So there's this change in dipole in both observations and models. In both observations and models, what was the integral change of precipitation due to deforestation? For it to integrate the amount, did it change?
That I don't know, because that's going to be coupled with larger scale changes in longer time scale modes of climate variability. Yeah, and so if you integrate over the region, that will be tied to many factors, and that's harder to parse out, I think. But you know, severe droughts have hit. You know, of course, in 2005 and 2010.
Much larger.
Yeah. But on the other hand, there were also very rainy years. I mean, 2009 was pretty darn wet, and 2004 as well. Yeah. So I don't know.
I'm sure there's some anomalies all over the forest area. They not necessarily even out.
Yeah.
So in your model, did you confirm the scale dependence of the dipole?
Yes, we did. I didn't show that, but we've carried out simulations with the different land cover maps and different model resolutions as well. And you can see very nicely how if you simulate coarser resolution, it blurs out. If you simulate finer resolution, I showed a little bit of that here. So, for example, the precipitation pattern, when you compress the deforested area, the dipole goes away, and you just get something in the center. And when you expand, it emerges.
Then did you look at the physical mechanism for the scale dependence?
Yeah, at the smaller scales, it's exactly the conventional idea that. Yep.
Okay.
Yep.
Then for the super large scale, then how about the suppression of the collection?
Yeah, and so we found so that's where the surface roughness comes in. So we have a divergence near the surface in the east, where you transition from rough forest to smooth pasture, which results in subsidence and
Yeah, that's for the medium scale. That's for the scale larger than 40 kilometers. Then
oh yeah. So we actually haven't gone beyond that. And the reason why we haven't done that yet is just because the actual deforested area hasn't expanded that large yet, and so we would have to make assumptions of what the area would look like, which would be a great thing to do.
So the scale happening right now is about 100 kilometers, or what's the size of the deforestation right now?
Yeah, so it depends with, in this direction, it is roughly about 100 kilometers. But, along the diagonal, I don't know, 400 or 500.
Not big enough.
Yeah.
Yeah, great talk. I think at some point you mentioned that the dipole was strongest in the dry season.
Yes.
When you were talking to the
Yep.
models, you mentioned that. How much stronger? And I may have missed it. If you talked about that.
No, I did not talk about the seasonality at all. And so the general idea is that the larger scale circulation is just much stronger in the wet season than in the dry season, and that just serves to damp out any local scale circulations that develop. And so we're actually right now working on trying processing the images for the GOES images for all seasons of the year.
Gotcha.
Yeah, and it's trying to link it to the details of atmospheric circulation.
I'm curious about the broader kind of context of
Yep.
your research, and since you introduced it in terms of some of the human
Yep.
natural dynamics and the implications in terms of human activity, and then of course deforestation as
Yeah.
a driver. So I'm curious just how you think about your research. Like, do you think about it as human natural coupled, and that's really what drives your interest in, and how would that manifest itself in the larger research program? Or is this more, wow, this provides a really great, deforestation in general and Rongonia in particular provide a really great laboratory for asking some basic questions about the mechanics of hydrocarbons. So,
I guess maybe from my own potentially parochial perspective, it seems like a lot of these modelers have been, including myself to a certain extent, have been decoupled from the human, the direct human feedbacks, and I think that's too bad. I think that we could actually, we may be, that by beginning to work together to bridge some of these divides, I think that there could be substantial benefits to that. And so while I haven't worked in that direction previously, I think that's actually one of the exciting things about this department, this institution, that may provide an opportunity to move in that direction.
So our team, a number of people here on our research group, we're working on a paper that looking at a massive drought in the Andes or east in Peru, more southern Peru, around in the 1790s. And we're all wrapped up around the mechanism here. And so the question, others in the group over here can weigh in. So we've been thinking about, well, was it something going on in the Amazon about that time? I mean, this is a multi-decadal drought, and it's well recorded in other places as well. particularly like out of the Pacific Basin and some islands, etc. And so we've been thinking about, well, could there have been a period of deforestation? Let's just say, for example, you know, I don't know, human-induced burning or just, you know, natural fires. I mean, we get lots of. But now, after seeing this experiment, and we're talking about the scaling, and the early paper to show when the patch gets over, say, 100 kilometers, then you know, conditions change. So I guess for us, we're trying to struggle with how large would the event have to be to make a massive drought throughout the Andes, as well as extending over to the tropics or to the tropical Pacific. And I know you wrote a paper recently about the teleconnection, if I can use that word, between what was happening in the Amazon, the deforestation, and the snowpack in the Sierra.
Yeah.
And I got really excited because I thought, well, wow, maybe we're not so far off that something going on in the Amazon may be responsible for this drought we're trying to understand. If it can affect the Sierra Nevada precipitation there.
Yeah.
I don't know. I just wondered if you had any thoughts. I guess the explicit question might be, since the scale in this study was small, how did you go about, you know, not in great detail, I have to explain it in great detail, because I'll talk to you at dinner about it. You know, what even made you look at the Sierra, and what's your general thought in terms of whether some massive drying event, or whatever caused it, whether, you know, I have no clue what might have caused this, could create a multi-decadal drought in the Andes that we have other proxy data telling us that it was also dry out in the tropical Pacific, possibly even all the way over to the Himalaya.
So, so I think that there's a growing number of studies that have looked at Amazonia that have considered cases where you have more deforestation than what I've shown, but less than complete deforestation. And so they have used scenarios, economic development scenarios that have been projecting 40 or 50% deforestation in the not too distant future. And they show something I think really interesting, that you could have substantial redistributions of precipitation, spatial redistributions of precipitation as a result of this partial but significant deforestation of the Amazon. And so, and so I do think that these sorts of land cover changes could change the way that change the atmospheric circulation enough so that you have more precipitation delivered here and less there. Whether or not that would specifically affect Peru in a certain way, I don't know. But I think stepping back more generally, it could affect South America. It probably will affect South America, and, but specifically whether it affects here or there, I don't know if we're at the stage where we can know that yet. I was motivated to look at the Western U.S. in that study that you mentioned, because I was looking at so there are different kinds of El Nino events. Some are more focused in the eastern tropical Pacific, some in the central tropical Pacific. And what it had seemed to me was that regardless of where exactly the El Nino event falls, it generally affects the northwest U.S. in particular in a certain way. And so I was wondering just how different deforestation of the Amazon is from an El Nino event, in the sense that both could potentially lead to heating of the tropical troposphere. And if it doesn't really matter if you have El Nino in the eastern Pacific or the central tropical Pacific, maybe it won't matter so much if you have an Amazon deforestation event causing diabatic heating anomalies and vorticity anomalies over South America. Yeah.
Very interesting. Thank you.
I was just going to ask you to speculate. So based on your relationship between the spatial heterogeneity of precipitation and deforestation, OLOM is just a circulation model. There is no coupled land model, right?
In these simulations, that's correct.
So if you were going to speculate, what would you think that the role of continued deforestation and the changes to precipitation, how would that influence the productivity of the tropics?
Yeah, I mean that's a good question, and in fact one that I'd be very interested in trying to answer. I don't know if I could give you a very sensible answer right now, other than to skirt around the outskirts and say that the answer will probably be sensitive to the spatial scale of deforestation. So you're going to want to control for that in a certain way, and that it's probably also something that we should be thinking about if we have reason to suspect precipitation may increase there and be reduced in a different location. It's something that we could be cognizant of in our planning. I just don't have that. I just don't know enough right now to be able to really answer that.
Thanks, David. It was really interesting how spatial patterns, scale, all very geographic and important variables are playing into your understanding of the dynamics.
Yep.
And I'm curious, you showed some interesting trends. I think there's some interesting enticement for a couple systems to think about how humans impact this. But if you were then to take just a stab at telling, I like the projection of what would happen if we deforest more, but even just think about some of the trends you've observed in rates of deforestation loss. Can you comment on what might be driving that, like human implications, and then maybe is deforestation the Amazon a good thing or bad?
All right. Yeah. So I don't think that you could call deforestation that you can label a blanket term, good or bad. It will certainly benefit some people and some trees more than others, and have positive benefits for some and negative impacts on others. Sorry, I'm getting a little bit lost in my thoughts here. So you're concerned with besides the good and the bad, or your question is?
Yeah, so you showed us a number of little intriguing entry points for where humans play into this.
Yeah.
Right? And so if I were to just basically throw that out there,
Yeah.
leads to where you might explore that issue of what's good or bad, what influences the actual deforestation rates, for example, you showed us the rate change.
Yeah.
That dropped off.
Oh, yes,
towards the
yes.
end of your,
Yes.
right? So it's
Yeah.
sort of thinking temporal scale now, and
Yeah.
human impact. And even this whole idea of syndrome, climate syndrome,
Yeah.
it's intriguing at title. Idea. When we think about human players in this climatic dynamics.
Yeah.
right?
So this is a direction that I'm interested in going in the coming years that I don't think has been adequately explored. So if you deforest a little bit, you'll maybe change the atmosphere, and that may affect your human decisions, and that will affect your deforestation, which will affect it's completely a coupled system. to my knowledge, I don't think anyone would say that that the changes in climate were the reason why deforestation slowed down. I think it's mainly economically driven, perhaps. I don't know specifically about Rondonia, but of course Red Plus was red, et cetera, was a big deal.
I'll just sort of throw it.
Yeah.
Maybe, system.
Yeah, I think I really think that's the future. That's we could learn a lot from exploring those interactions. It's definitely an understudied approach. Yep.
So most of the land cover change was to great pastures, right? So grazing.
In
Is
this
that right?
particular area.
In this case, yeah. So I just have a question on the magnitude of these changes. So if you're a farmer and you're grazing crops on the east side versus the west side, are the changes in precipitation enough so that you're thinking, man, these guys are getting all my water? Or are they just maybe smaller so that maybe they just impact the crop years?
So there is, all of this is occurring within the backdrop of climate variability,
Sure.
which is substantial.
Yeah.
And so I don't know if, I don't know to what extent people may have linked any particular changes with.
But are the magnitude of the changes enough to be potentially, how big are the magnitude of those changes? A couple percent or bigger, I guess? And I see, but these are differences from aerial means, so, yeah, anyway, it may not be a well-formed question.
Yeah, I think the differences are substantial. I definitely think they could be impactful.
You have this, seems to be a very local process, yet you chose to go look at it with a global model.
Yep.
And you lost resolution there. Why did you not go with a local model that, with the more, synthetic settings, at least for the exploration of the generation of life? Because then you could have looked around it. You didn't have a resolution that would resolve convection, for example, 500 by 500 grams, you're going to do a longer resolution. So I was curious in your choice of a global model to explore something that was, you were feeling was very local effect and a local process with a local response. Right?
Yeah. So the cost of going to the global model is not as great as you would think. And so. 500 by 500 grid cells, was at 2,500 or so total. And so maybe this is twice as much.
But then you have 1 kilometer resolution for your collection. That's why I was just thinking, right? Because you go look at clouds directly.
That's a valid concern. So the problem that we found, especially in the Amazon, is with prescribing adequate boundary conditions for these models, especially near the Andes. And so what are you going to do for your boundary conditions? Reanalysis, probably. And especially since the complicated topography is so near, we've actually had trouble with our limited area model simulations of the Amazon compared to these global simulations, precisely because of the boundary condition issue. And so I guess maybe this is being overly conservative in treating the problem that way, but at least we got rid of it.
No more boundaries.
Just one quick question about the sort of the mechanics of how you did one aspect of this. I noticed you have a fine granularity of your cells, and people study very interesting, and they get larger. Did you custom build that, or is there a way that you can say, I'm going to put a scope on this area and less so on the edge. So if you change this study to, say, Europe, could you rebuild data over Europe? And do you have to get data to populate all these big cells, or are they all from models?
So that would be trivial.
Yeah.
Yeah. So that's set by the user at runtime.
Okay.
Yeah. So you,
What I'm thinking is, if I take a study area and I decide I want to get a lot more resolved, that quadruples or multiplies the amount of data I need for all those small cells. So you do not need sort of separate observable data for all of the smaller pixels, or those model parameters for every cell.
yeah. So just to make sure I'm not confused. So this is simulated. So it's the model that's simulating the atmosphere here. The observed data that go into this, probably the most important one isn't even shown on this graph. The most important observation that drives this are the sea surface temperatures. Okay.
They're off the edge of the data somewhere,
Yeah. So you need the global sea surface temperatures, and you need to specify the land cover properties of each grid cell, so things like the roughness length and the albedo. And if you want to take realistic contemporary conditions, those maps exist. And so if you wanted to do a study of Europe, we're also interested in Central America, how the substantial deforestation that's been occurring there is affecting, they're potentially affecting the atmosphere. That should be, I see the transfer papers.
It was quite powerful. We might have time for one more question before we wrap it up. So, one more?
Okay, so
Oh, good one, Jim.
so how well does your model simulate the large scale flow, the mean climatology?
Yeah, so so we have several papers that have looked into that. So we run all the standard Held-Suarez experiments, etc., shallow water tests, simple cases of flow over mountains and things like that. And so, how well does the model do it? That's excellent.
Well, let's thank Dr. Medvigy for an excellent Remind everyone, it's a busy day. We do have another guest speaker in the Robinson Lecture Series, but we do have also a chance to meet with David during the mid-morning hours, so a chance to chat then. Actually, it's early. It's early.